this was on when we first came in. Yeah, no, that's doing it. Okay. Yeah, that's doing it. So.
All right. Go crazy. Just roll this too loud.
So do you have a name yet?
For the dog?
Yeah.
Boone.
Boone.
Boone. And we're debating whether or not there's an N on the end, an E on the end, whether it's a B-O-O-N-E or B-O-O-N.
You say M or N? N.
It's B-O-O-N and then E question mark. Could have been an M.
Why does this not go down? Or is it up?
It might go down.
Like this thing here?
That should be the screen. If that doesn't work, the one on the left will raise the projector. You'll have to stop it.
We want to lower it, right? Oh, that's going on. Oh, no, there we go. Yeah, yeah. Oh, nicely done. Okay, well, I guess we'll get going. I'm Alan Calder, and I'm going to tell you all about astrophysical flames, or how I learned to stop worrying and love thermonuclear explosions. And I want to say from the outset that I'm putting together a talk that represents a lot of work by a lot of people. I do not want to take credit for all of this research. I'll try to mention names as I go through. But I'd like particular to mention Aaron Jackson, Brendan Kruger, and Don Wilcox, who have been the PhD students I've had the good luck to work with. And my collaborator, Dean Townsley at the University of Alabama. We started out together at the University of Chicago. Mike was there as well, and working on the developing of this flash code. And that has continued to go, and that's the recurring theme, is that much of the science you're going to see here was done with that code. And Dean has been my collaborator in the astrophysics for about the last 13 years. So this is meant to be an interdisciplinary talk. I strongly encourage asking any questions along the way. I've got more material than there is time, and I'm happy to digress into the ins and outs of some of it. I'm going to tell you about the basics of flames and what they are, and then modeling the flames. And it turns out that thermonuclear flames in a white dwarf are impossible to directly simulate if you also cover the simulation of the star, and I'll show you the length scales and all that. So you rely on models, and then I'll talk about the role of flames in the context of blowing up a star in a thermonuclear supernova, and then I'll end by talking about post-processing the results. With the model, you get bulk energetics, but if you need to get detailed abundances out of your calculation to, say, put together into a spectrum, you have to post-process the results to get that. And in the Shakespearean sense, and I learned the phrase meta-theater in getting ready for this, but the play within the play is subgrid scale modeling in a multi-scale multi-physics object. And it's an astrophysics application, but that's what the computational science is. Okay, so I've got some notes here that I can't really see, so I may flip to that. I'll pose a question, what is a flame? If anybody wants to jump up with an answer, we could probably skip a little bit. Okay, so it turns out that's a bit of a subtle question, and it was the topic of a challenge that Alan Alda, who is the big cheese behind the Center for Communicating Science here, posed a few years back, because he wasn't happy when he asked the question in grade school, and the answer was, oh, it's an oxidation. Well, there's a little bit more to it. And the winner produced a 7.5-minute video that's available on YouTube all about a flame, and it talks about chemiluminescence and the fact that the blue part is because the atoms and molecules in the thing are hot. The yellow-orange is because there's soot that's glowing, so that part is thermal. But that's more like a terrestrial flame, and it's describing basically what you see here. So that's not quite what we want. I looked it up in the American Heritage Dictionary, and I got the zone of burning gases and fine suspended matter associated with the combustion of a substance. Getting a little bit better. I like their last definition, informal, a sweetheart. Not quite our definition either. So when you can't figure something out, what do? You ask the Wikipedia. And the Wikipedia gets into what I'm interested in. It is stuff. They talk about the terrestrial combustion case, but it's things caused by a highly exothermic reaction taking place in a thin zone. And the thin zone is what is the important part to modeling the flames. And so there are two broad classifications of burning fronts that we can have, and it has to do with how fast the front propagates. If it's subsonic, meaning slower than the speed of sound, we refer to a flame like that as a deflagration. And if it's supersonic, it is a shock wave propagating at the speed of sound or greater, then that's a detonation. And so here is one of the, in my not so humble opinion, the coolest commercials in the history of man. It's a look inside a high-performance like M3 BMW engine. And this illustrates a flame very nicely. Now, fuel injector comes in, 2 intake valves, that's 4 valves per cylinder, you know it's high performance. Spark plug's going to go, and woof. Here's the physics of it. You've got this relatively thin burning front propagating in 3D subject to instabilities. And that's what we're going to declare a flame. And it turns out that for blowing up a type 1A or thermonuclear supernova, the details of that are extremely, extremely important. Now, I fancy myself a bit of an armchair car guy, and if people may remember, there was a talk about some work being done here on internal combustion engines, and I asked the question about detonations. That's what happens if you detonate in that cylinder rather than having that nice deflagration. You get a shock wave that'll go and it'll break the top of your piston. And that I want you to visualize these two extremes, something that's just kind of propagating along and something that's going like a shock wave.
Which way does the piston go?
So the piston, these are the rings down here, and it goes up the cylinder like that.
So that's the piston head.
That's the top of the piston, yeah. And a detonation blew the top of it out. And
I didn't realize it was hollow bond.
oh yeah, no, it's you could turn them over and they make an ashtray in a lot of shops. But, questions on anything so far? Please don't hesitate. I mean, I'm throwing a lot of vocabulary and stuff like that. Okay, so a little bit more. A deflagration is combustion of a material that propagates at subsonic speed. That's what we're going to call a flame. We're going to refer to a detonation as a detonation. The Lewis number is the ratio of thermal diffusivity to mass diffusivity, and I'll illustrate how that works. And in astrophysical flames, the flame propagates by heat conduction. This number is much larger than that, so we say large Lewis numbers, where terrestrial flames have a Lewis number of the order of unity. That means that mass diffusion, mixing, is about as important as heat conduction. But deep in the core of a star, the equation of state is degenerate. It's degenerate electrons that provide the pressure support, and they're very, very conductive. And detonation, again, that's a rapid combustion at supersonic speeds. Now, these are the same words, so we're not going to worry about that. But this is a look at a flame where the dotted line is the fuel abundance. The flame is propagating in this direction. Here's the temperature. Now, this is an astrophysical flame where heat, if this is the reaction, heat is propagating out that preheats the material until the reaction begins to go at some threshold temperature. You're consuming fuel, so its abundance drops down. The temperature continues to increase until you consume all the fuel. And then you've got a steady state behind it, assuming it's not having a density gradient or anything like that, at a given temperature of the ash. And this deflagration and detonation transition, the change between the two, is one of the things that's in the realm of basic physics that we think is involved in the story I'm going to tell you about the astrophysics, but I'll come back to that. Question?
Yeah, so maybe a naive question.
No naive questions.
So I understand the difference between deflagration and detonation in a terrestrial setting, but when you're in an astrophysical setting, you're in outer space. So the speed of sound is what?
So in a vacuum, there is no speed of sound. That's exactly right. But in astrophysics, I mean in the interior of a star. And so it's, just think a very high density gas. And so you can have subsonic and supersonic going exactly the same way. And that's a good point. The flames I'm talking about in the astrophysical setting are in the interiors of stars. No, that's a great question.
Where is the transition between subsonic and supersonic here?
What's that?
Where is the transition between...
There's not. I'm just saying that that's coming. This is a slide that has these words on it, and it's coming. I'm going to look at I'll show you one way to do it. Now here's a look at the detonation. Fickett and Davis is a classic book. And their first division in the detonation case is whether it's unsupported or overdriven, and that has to do with a piston following it along. One of the tricks to a detonation is that it either has to have something going behind it to support it, or it can weaken, the shock gets not strong enough and it can quench. And I'll just make a point about detonations that the overdriven case, you've got a piston, you've got roughly a steady flow and then a thin reaction. In the unsupported, you've got a thin reaction and then there's a bit of a rarefaction. And as far as we know, and this may have changed since I last discussed the issue with people, but detonations occur in a confined environment. And one of the open research questions, and I have talked to people, Alan Kirstein, for example, at Livermore, about whether or not you can have an unconfined detonation. And people would love to be able to do an experiment of, say, go out over a big field somewhere, spray out all sorts of fuel, and see if you can detonate it without it being in a confined space. Here's a look at a detonation. This is an astrophysical case, but it's a direct numerical simulation. You've got carbon fusing here, and this is in a box with periodic boundary conditions, and you wind up with the transverse waves going wrong. This is a shock wave here, but there are similar waves going like this. And you get this sort of scale structure, and we've seen such cellular detonations in mine explosions here on the Earth. So the takeaway here, yeah. Yes. The simulation, it's 1, 2, 3, 4 of these, and then it repeats on these sides. Blue is unburned carbon, and then it's a very thin reaction that initiates, but depending on where these transverse waves are, you get what we call triple points, where there's a high density, and it burns there. But eventually, it all is going to burn. So what I want you to get out of this is that even in the detonation case, where there's a shock wave going through, multidimensional effects are important. When you see it in the textbook, whoops, it's always shown like this, but even in the case of a shock, the multidimensional effects are important. Okay, so now we've established deflagrations and detonations. this is what we see when we do an experiment with astrophysics. I'd love it if I could, but it's not in my power to conjure up a stellar explosion in a laboratory. So what we do is we put telescopes. This is a different galaxy, and you're going to see a little simulation where something suddenly brightens up. This is the light curve, and the little yellow ball marks where we are. This is on, say, on the order of a month going this way, and this is a simulated spectrum. And so this thing rises, gets very bright, and then drops off and decays over a few weeks. This? I thought this was just something that Peter Nugent whipped up. No, this image isn't simulated, but the little thing getting bright. No, that's a real galaxy image, yeah.
Well, no, that's a real star, supernova, too.
Are you sure? Okay. Okay, well, I stand corrected. That's a supernova going off, and here's the light curve, which you can think of it as just a count of all the photons, the brightness over time. And then you look at the spectrum as well. So the question is, I've referred to supernovae, and I've referred to type 1a supernovae, and you heard the word thermonuclear. Type 1a is the spectral identification. Thermonuclear is the mechanism. And the question is, how do you blow up a star in a thermonuclear reaction? And there are three main models under investigation. All of them involve a compact star known as a white dwarf. And that's a star that has about 1.5 times the mass of our sun, maybe not quite that. And it's an object about the size of the Earth. It's compact. And there are three ways we think we can do it. The so-called single degenerate Chandrasekhar mass is you have a white dwarf, which you can't see here because it's so small, but gravity is pulling material from a companion, and it gains mass. It begins to simmer, and then it eventually explodes. And there's a limit on how massive it can get because the electron pressure support, and Robert, I sent you something about this a long time ago, but the idea that electron degeneracy is supporting this thing, basically that means you can't squeeze the electrons in any tighter, and there's a limit that you can get there, but the thing blows up before that. Then you might be able to merge two white dwarfs. We call that the double degenerate. And the degenerate, that means that electron pressure support. It's describing the dense stellar material. And it's possible that you could have two of these. We have a former grad student now at NVIDIA, Max Katz, who worked on this as part of his dissertation. And then there's another case where you have the accretion like this, but it's not as massive, where the accreted material gathers on the surface, a detonation happens in that shell, and that triggers a detonation in the underlying star below. So there's a lot of vocabulary, a lot of astrophysical stuff, but what I want you to take home is that this type of supernova, which we believe is thermonuclear powered, involves at least one, maybe two, compact stars known as a white dwarf, and it's a flame propagating through that is actually may transition to a detonation that explains the explosion. Everybody with me on that? Now, if you know any astronomy, you're probably saying, okay, well, wait a minute. Don't supernovae make neutron stars? And they do, but that's a different class. That's the core collapse mechanism, which is the way a very massive star goes out. This is the thermonuclear case. So, just to show you, here's this I'm sure is a simulation. But here's a star. It's a main sequence or red giant. Oh, that's supposed to loop. And yeah, they seem to have updated PowerPoint to make it better. Like I said. Anyway, the idea is that it gains mass from a companion, and the white dwarf is something the size of the Earth just right in there that you can't see. So here's the schematic of how this works. You've got almost 1 billion years of accretion onto this compact star, and that's a tricky problem to evolve. We can get steady state models in 1D, but this really isn't a 1D object. As the mass approaches this Chandrasekhar limit, it gets compressed, the interior heats up, thermonuclear reactions begin to go, and there's a period of smoldering for about 1,000 years. And then at some point, this thing is convective. You've got material rising and cooling, descending and heating. and reactions are going, it's slowly getting hotter, but at some point it gets hot enough that the cooling from the rising isn't fast enough and the reaction goes, and eventually that flame will incinerate the whole thing. Now, at the highest densities, and I'll illustrate this, the flame is that wide, okay? This is an object the size of the Earth. That's why we need the subgrid scale model.
So when you say that, why do you mean the size of your thumb?
Literally the size of my thumb. It's a sub-centimeter. I mean, even smaller. And I'll show you some direct numerical simulation of these things.
What is in the smoldering region?
What is the smoldering region?
Yeah.
It's in the interior of the white dwarf. This is the white dwarf, and there's convection.
When it compresses, what is the product?
The product, you start fusing carbon. It's a star composed principally of carbon and oxygen. Carbon fusion, carbon-12 plus carbon-12, goes to several things that we'll just call magnesium-24. It's a well-defined carbon fusion reaction. The product is magnesium.
Doesn't it go up to iron?
That's coming. Hold that thought. Hold that thought. Okay, so then you can simulate the explosion, and eventually, to make contact with the observations, you look at the light curve in the spectrum. And in order to know that, in order to calculate a synthetic spectrum, you have to know the abundances all the way up through iron and stuff like that, and their relative proportions and how they're laid out in the expanding remnant. And that's what we want. So typically what we do is we take a parameterized white dwarf that has gained mass from the companion. There are some reactions that go on in it. Don Wilcox's his dissertation is going to solve the problem of the nuclear physics of this smoldering. And I'm staring at him because he wants to graduate. And then the explosion we model was something like this flash code that I was talking about. And then you construct spectra and light curves from the evolving expanding remnant and compare that to the observations. So here, this is a look. You asked about that. You asked about the smoldering in there. There's a lot of nuclear reactions going on, and this is Don with Desmond, if you guys remember, he was a summer student, looking at the production of A is 23. Is that sodium or neon? It's actually, I guess it's producing sodium, right? Yes. Anyway, you've got convection going on, and you get an electron capture that kicks a neutrino out. It rises to a lower density. It kicks an electron back out and a neutrino, and it's called the Urca process because, like a casino, the house always wins a little bit. The neutrinos always lose and acts to cool. And we want to understand that nuclear chemistry going on. And Don is working on modeling this process with a network that he and other collaborators have developed for the Maestro subsonic full 3D stellar evolution code. And this was a nice bit.
Are those rings?
So the way the colors worked is that these are volume rendered surfaces representing thresholds in the production of that element, if I remember that right. The way Desmond described it was that he had several surfaces. So you can think of it as just putting a color and an opacity to describe a certain region of the reaction. Okay, so this is deep in the core of the star, and when that explosion starts, even though it's degenerate, it gets so hot that it degeneracy lifts, and you've got a flame propagating out from the center, possibly, into a cold carbon-oxygen white dwarf, and this surface is subject to fluid instabilities. And to describe this right, you either need to fully resolve that, or you need to have a subgrid scale model. Now, our codes work with adaptive mesh refinement, and I'll illustrate that in a second. That means that essentially you put more grid zones near the sharp features so you can better resolve them. But even that isn't enough. And so here's an example of the basic physics of this. This is the Rayleigh-Taylor instability. Lord Rayleigh from the 1800s and G.I. Taylor from the 40s. And the idea is if you have a dense fluid, that's our cold fuel, on top of a light fluid, that's our warm expanding ash, with gravity pulling down, this is unstable. And you can imagine this. I mean, bubbles are going to rise up and spikes are going to descend. And this Rayleigh-Taylor instability is actually a problem that's in the realm of understood but not completely solved, because it's an inherently multidimensional thing, and you look at the growth of that mixing zone where the spikes and so forth, and it was arguably this instability that they didn't properly model right that led to the National Ignition Facility not igniting as they expected a few years ago. And I'll show you, here is a simulation of this Rayleigh-Taylor instability. Now, this is a two-dimensional simulation where each block like this is an 8-grid zone by 8-grid zone region of space. And as you can see, you put more of them at this sharp interface. Okay. Now, here we go. So here, this thing was just perturbed. These little instabilities begin to go. And it's 2D, yes, but even in 3D, you see an inverse cascade from small scales to large scales. And that's one of the ways that the Rayleigh-Taylor is unusual. And eventually, a single plume begins to dominate in a single rising bubble. Okay, now it's quiz time. Let's go back here. So here is our hot ash. Here's our flame that's Rayleigh-Taylor unstable. And here's the instability growing. In this simulation, it was just two fluids. But if this were the burning front, how is this fluid instability growth going to affect the rate of burning? Anybody want to guess? Well, the large Lewis numbers flames propagate by the conduction of heat. So if you twist the flame front up so it has a larger surface area, more heat can conduct. So it boosts the burning rate. And if you think of it as just a measure, in this case it's a length, but if it were 3D it would be an area. If you think of just the burning rate being proportional to the area, then you could imagine that as this gets all stretched around, already I've driven people away, as this gets stretched around, the burning rate gets boosted. And so here are the length scales. You can look at this. This is in centimeters from 10 to the minus 5 to 10 to the 11. And that carbon deflagration is this blue curve here, where this is the density. So in the very core of the star, the carbon flame is like 10 to the minus 5 centimeters. This dashed line is the radius of the white dwarf, which is about 10 to the 8. And the black line here is what we can resolve in a simulation. So what we want to do is capture that unstable flame. It's occurring on scales like this, but in a model where we can resolve like that. And that's where our meta-theater, the play within the play, comes in. So here is a direct numerical simulation of a flame propagating at a high density, 10 to the 9 gram per cubic centimeters. Carbon and oxygen, which are the two components of the white dwarf, the fuel, are in our Christmas colors here, and the flame is propagating this way this time. They sort of alternate. And Pedro, you asked me the question. So here, the first thing to burn is carbon, and 24 magnesium, that's the green curve, 20 neon, and some heavier stuff. There's helium. But you consume that, then you consume the oxygen, and indeed, exactly as Predrag anticipated, you work your way up the periodic table until you get to iron group stuff, particularly 54 iron and 56 nickel. And it turns out that the 56 nickel is radioactive, and it's the decay of that that powers the light curve. And so the trick is to get just the right amount of nickel 56 to match the display. And I'll show you how that works in a second. So here is a nice schematic. This is a detonation that Don ran when we adjusted the burning to run a slightly different type of white dwarf model. And it looks like the same thing. Here, no longer Christmas colors, but red and blue. And then you get intermediate mass stuff that comes up, and then it goes into iron group stuff. So a little bit of the physics of this. The fuel is carbon and oxygen. Behind that is the ash from that, which is going to be roughly A is about equal to 22 or 24. And then you get into silicon, which is a nuclear statistical quasi-equilibrium. It doesn't just burn to that, and that's the ash, but it's a hot soup that's in an equilibrium. And then you go to nuclear statistical equilibrium in the iron group stuff. Okay, now I know what you're saying. Okay, who cares? It's iron, it's inert, what's it going to do? Well, the answer is that it's actually important. And so we want to describe that. So I've shown that we have to have a model, and here's what we do. We do a thick flame. It's not a thickened flame. In the combustion community, a thickened flame means something that you artificially make thicker, but it describes all the reactions that you want. This is a model flame. And it's based on an advection diffusion reaction scheme where the width of the flame is tied to the grid zone. It's 4 grid zones wide. The flame speed is an input parameter to the model, and you take the maximum of a laminar, that is, you just do a direct numerical simulation like I showed you and measure it, or a turbulent model speed, which is based on that Rayleigh-Taylor instability and also background turbulence. As you saw in that simulation of the Rayleigh-Taylor, things begin to move every which way, and that generates turbulence, and that's going to boost the flame as well. So the energetics of this model are described using the previously detailed calculations. I showed you that direct numerical simulation. And you have to have a special simulation with a different type of code, an equilibrium code, and Ivo Zeitenthal ran this to describe that ash in nuclear statistical equilibrium. Question?
How do you know the composition of the reactants?
How?
So, as an initial condition, you have to set some reactant composition, right?
Yep. So what you do, let's use this as the schematic. In this case, the detonation is propagating this way. And your initial conditions are a little bit of neon here and carbon and oxygen. Okay. This was performed with a simulation that had quite a few isotopes in a reaction network. And you just actually are doing a direct simulation of it.
I think he's asking, how do you know it's carbon and oxygen?
Well, how do you know it's carbon and oxygen? Well, so there, you go back to stellar evolution, and you take a star like our sun, and for most of its life, it burns hydrogen into helium. And then once it gets a helium core, it contracts, and the helium begins to burn. And you could think triple alpha, and eventually you wind up with carbon in there. And unless you have more than about 8 times the mass of our sun, burning stops right there. When our sun ends its life, it will be a carbon-oxygen white dwarf. And that's pretty well accepted from the field of stellar evolution.
Do you know if it's a homogeneous mixture?
So, the answer is, we think it's not homogeneous, that for many years we assumed it was 50-50 carbon-oxygen, but more recently, and I'm staring at Don because he did this, stellar evolution says that you can get incomplete burning and you can get a convective boundary region that causes the flame to quench, and you wind up with a distribution of things. So let me see. I don't want to digress too long, but let me see if I can find. I want to see if I can find one of Don's models. I may not have it in this talk. No, I don't. But that's actually, Don's dissertation involved huh?
Will involve.
No. His
When it's written.
his first, no. But so when he wanted to be my student, I threw him in the deep end of the pool and said, here's a problem. The first thing he did involved taking a non-uniform white dwarf, adapting the code to handle the burning for these extra species, and then blowing that up to see what would happen. So that was chapter 1 of his dissertation. The bulk of the work he's still got to do. Does that answer the question? Okay. So let me go back here. Okay, so I won't force feed it, but these are the equations of hydrodynamics, the Euler equations. This is continuity, conservation of momentum, conservation of energy. You close it the system with an equation of state that describes the pressure as a function of density and energy. You solve the Poisson equation for self-gravity to get the local acceleration due to gravity. And you can also advect a scalar, which looks a lot like continuity. And the code has the ability to advect something like that. And for those who might be engineers, some people call that convec things, but it means fluid flow. In astro, convection is when it's driven by heat. But I know some engineers say it just convex along, but advect is the word I'll use. And we use that to build an advection diffusion reaction scheme where this is a reaction progress variable that advects. There's a diffusion and a reaction where you've got two coefficients, kappa and tau, that are artificial. They're not physical, but they're set so that this thing will propagate a flame at the input speed that you give it. It is a model. It's not a physical calculation that's doing it. And there are several things you can do for the reactions. You can just say it's a top hat that in a certain region of this progress variable it reacts. That turns out to be pretty noisy. This is a so-called KPP, where the KPP are Kolmogorov. I wrote it down so I could say it. Kolmogorov, Petrovsky, and Piskunov. And what we found was stable and quiet was the so-called shifted KPP, where you put a couple of little epsilons in there. And that reaction produced a flame that would propagate at the speeds we could tell it to do, and it was quiet. And so that's the basis of our model.
Are you really solving four-dimensional equations?
Yes. It's a split scheme, but we're solving the full case.
What is the symmetry?
There isn't a symmetry.
So it's complete.
Should be, yeah. We don't assume it. This is what this reaction progress variable looks like. It has a nose out here because it's diffusive. The reaction turns on in some number of grid cells. 4 is what we set it to. This is the top hat. The KPP would look something like that. And then it goes from 0 to 1. 1 represents completely burned. And then we describe this in the model as, and the flame is propagating this way this time, burning the carbon produces about 50% of the energy. That goes to magnesium. The magnesium and the oxygen burn, that produces about 50% of the energy. And then it relaxes into NSE, where that's in equilibrium. And as it moves in the star, the burning energy changes. It is reacting, and that can release something like 50% of the energy as well. Okay, you're saying, all right, Mr. Smarty Pants, you really have lost it here. That's 150%. No. Releases energy, releases energy. Energy depends on the state. It can release or absorb up to about 50% of the energetics that we're talking about. Now, this is a full three-dimensional simulation of a flame that was born near the center of a white dwarf. And you never want to admit when you're wrong, but I was wrong here. We got the energetics of the flame incorrect. We didn't properly treat that ash in equilibrium. We assumed it went all the way to nickel. And this thing was so hot that as it rose, it went transonic. And you see this out here. That's a shock. When shocks go through things, they heat them up. And we were very excited about that because, as I've hinted at before, we think that a deflagration to detonation transition is part of this process. So we got to playing with that. We realized we made a mistake, but then we discovered that you might be able to actually blow this thing up. It turns out you've got this convective interior, and it's very hard to get a small region of burning to just burn out. It always wants to rise. But look at how we found. This is called gravitationally confined detonation. And this is how we found you could blow one of these things up. You have a fireball that rises. Now, this is just a volume rendering like we saw before. It represents a certain density. Now, it should be smooth. My laptop can't quite cut it for this movie. But this is hot burned material, and ahead of it, like a snowplow, there's other material. And right there, you get a compressional heating. Okay? And we actually studied the basic physics of this. This model can't capture it, but Ivo Zeitenthal did a study on compressionally igniting detonations. And boom, just like the blown piston, a detonation goes through, And physically, faster than that movie played, in 1 second, that detonation goes through an object the size of the Earth. Okay. And so that's an example of an explosion that involves a deflagration to detonation transition. And that all came about because we got the energetics wrong and saw that shock and got excited about the fact that we might be able to make that transition. So that's one way to do it. Now, let's go back to the basic physics. And this is work that Mike Zingali did some time ago, exploring that carbon burning. Now, the flame is propagating up this way. The red is carbon. The blue is, it's just magnesium, right? It's just a magnesium ash. And all that's different between these simulations is that the density is decreasing. You go from 1.5 times 10 to the 7 grams per cubic centimeter to 6.67 times 10 to the 6. Question? Well, here's your chance to argue with me, so go for it. So this I don't know what the Reynolds number is here, but
The resolution is the same.
the resolution is the same between the three. The only difference is that the initial conditions were at different densities of the fuel.
I was thinking of the density, not of the fuel, but everything.
Well, of everything, right. But the material behind is going to be a slightly lower density, but these are the densities of the fuel. And the reason why the simulations turn out different is because as you decrease the density, the flame speed slows down. The flame speed slows down, so instead of getting a nice, well-defined flame, that Rayleigh-Taylor instability has time to develop. At the high flame speeds, fire polishing, it's unstable, but it keeps a nice, steady flame. But as the flame speed slows down, the Rayleigh-Taylor instability begins to take over, and you get this very, very wrinkled up thing that actually picks up burning speed. But the point is, we want to be able to capture this, the physics of turbulent flames, any transition to a detonation, and all of that. And you really need to do it in 3D. So what we did was put the model flame through a process of 3D testing. And so here, these are two test simulations of a flame burning through a channel, and it's moving up like that. And the only thing that's different here is the input flame speeds are different. Everything else, the density and all that are the same. So in the flame speed of 1 times 10 to the 6, you have more Rayleigh-Taylor instability. At twice that, 2.14 versus 1.07 times 10 to the 6, it's smoother because you've got more of the fire polishing. But there's more area here. You've got twice the surface area. So the overall rate of consuming fuel goes as the flame speed times the surface area, and that's constant. These two wound up consuming, you've got half the flame speed, twice the area, the product is the same. And this is a property of these types of flames that we wanted to see if we got. It's called self-regulation, and we can express that as a scaling law. So here's a simulation of the flame front speed in kilometers per second. Up here is the effective flame speed measured by knowing the area and scaling it. And what you see is that at fairly small flame speeds, the actual flame speed goes as the scaling law. It's the square root of AGL, where G is the acceleration of gravity, L is the width of the channel, and A is the Atwood number, which is the difference in the densities across the flame over the sum. And if you remember Atwood's machine from basic physics, it's the same logic. And so down here, it's self-regulated. This is a measure of the variance of it. But in this region right here, indeed, we saw that the consumption of fuel was independent of that input flame speed to the model. And that was what we expected. It would obey the scaling law. And then we ran it through a bunch of tests where we changed the input flame speed. We took half of gravity. We put it in a wider channel. And it always did it. So the dashed line here, this is time versus the burned mass, you always see good agreement with what that scaling law predicts. The alpha is a coefficient that we measured to be a half. So this is a verification test showing that under a whole host of different circumstances, we were able to match that scaling law. And here's a resolution test. We get the same result. It converged in resolution. Now, some busy slides coming up. I mentioned the change in area. Curvature is very important to a flame. And there's a wonderful paper in the Astrophysical Journal by 2 graduate students at the University of Chicago, the effect of curvature and stretch on flames. And I'm looking at Mike. He and another student took the initiative, and it was really a cool. I was lucky to be part of that project because they came up with a good idea and went and published their own paper as graduate students.
That other student will be here.
And, he's coming. Jonathan Dorsey's coming to talk to us. He's in another field now, but he's coming to talk to us about computational genomics and things. But anyway, if you imagine that this is the heat conducting out of the flame, in regions where it's convex, you get a concentration of heat, and that boosts the burning. And I'll just say that if it boosts it in a sharp curved region, or over here it expands, it slows it, that works to stabilize it. And here, this is a measure of the curvature, and you can see this is the flame speed. The more curved you are, the more that changes. And this artificially thickened flame has a real problem with that, and a guy who was in the group in Chicago named Shimona Sita coded up this big icky thing to correct it. And here's before. You get a very smooth flame, but with correction, you get small-scale structure that you would expect. And we came to the conclusion that that was very, very difficult to implement, but you want to be aware of the limitations in curvature. Here is a direct numerical simulation by Jonathan Dorsey, again, the guy who's going to come and was a student in Chicago, of a flame hitting a vortex and stretching it all around, and that's going to boost the burning. And then Aaron Jackson, a few years ago, took a terrestrial turbulence model, adapted it for the large Lewis numbers of astrophysical flames, and then came up with a subgrid scale turbulence model that could boost the flame speed. And these two are the same simulation, but with a different contribution due to the turbulence. And you can see that's an isosurface describing the flame. And there are different sizes at the same point in the simulation, so you see that it has a physical effect on that. This was just a flame propagating through a box of turbulence. And we put all that together, and here's what we have. We use this ADR scheme to propagate a model flame with a specific input. The laminar flame speed comes from a one-dimensional detailed calculation. You've got subgrid scale models for the Rayleigh-Taylor, that square root of AGL. You assume that's happening on scales you can't resolve, so you use that turbulent flame speed. And then we adapted that turbulence model. That gives you another input. On the large scales, it captures the Rayleigh-Taylor. We saw that self-regulation that we expected. The flame model is coupled to the appropriate energy release for the 3 parts. It's a 3-stage flame, and it lets that ash in equilibrium evolve. And then as I showed you, we do all these tests as best as we can, and we found that sharpened KPP flame was nice and stable. Okay. Don't worry, I'm not going to run over. Now, I keep saying DDT, and I showed you that model where the compressional heating happened. But if we think back to our case of the race between fire polishing and the Rayleigh-Taylor instability, as a flame becomes wrinkled, several things can happen. One, you can wrap, now the fuel is in red here, you can wrap a pocket of fuel in hot ash and it'll cook off, and that could ignite a detonation. Some people say that you exceed a certain fractal dimension, and that means you've got enough surface area that your net burning rate exceeds the speed of sound, and that's a detonation. Or some people call this a regime of distributed burning, where the net burning rate exceeds the speed of sound. The point is, in the right conditions, we think that a flame just propagating subject to fluid instabilities and perhaps the proper gradient and a few magic words there's a Zadovich mechanism where the fuel is prepped in a certain way with a gradient into the ash, that transition can happen. And I think I covered all that. Now, the last point to make is that this behavior is a function of the flame speed. And in the real star, and this goes back to your question, this is very important. In the real star, it's not just carbon and oxygen, but you can have some things like neon, and that affects the flame speed. So as you change the composition of your white dwarf, the dynamics of what you're going to do changes. And I'll illustrate that with some simulations. So here, this is a two-dimensional simulation where we assume that wrinkling is going to cause a detonation transition at this radius marked by the green contour. This is deep in the core of the star. This is the radius in times 10 to the 6 centimeters. And this is an initial match head that we let off, where we have perturbed it to make it unstable to these fluid instabilities. And so here this thing goes. It's a deflagration. Now notice that the star is expanding, okay? Now, it's a model, but we assume that when the flame hits this low density, the wrinkling triggers a detonation, and boom, there it goes. And there's a second one that's going to come here. Okay. I said that, and you anticipate this. This is really good. And Predrag too. The iron group stuff is the final ash. And I said that nickel 56 is radioactive, and that powers the light curve. And the next movie is the same simulation, the same color scheme, but here we're looking at the variable that describes the relaxation into nuclear statistical equilibrium, and that is the iron group stuff. Okay. The amount of iron group stuff includes the nickel 56. That sets how bright the event is going to be. So here, the same simulation, but in this case, what you're going to see is the burning only goes into the high density regions. So it's going to make that same transition. It's the same simulation. But you see nothing's burning out here. It's only in the high density regions, and you see how the star is expanding. So here's where we put it all together. You change the flame speed because of the composition, and that changes how far out you have to go before that detonation occurs when the flame gets wrinkled up. That changes the amount of expansion. That changes the amount of stuff that's in the iron group. That changes the brightness of the event. So we can put that together, and here, here's a series of simulations. This is the mass of material in the nuclear statistical equilibrium, the mass of the iron group stuff, versus time. All the simulations are from the same initial condition, but we changed the threshold density, which would be equivalent to having changed the flame speed. And what you see is you get a nonlinear decrease as this density changes to lower and lower. You get a nonlinear decrease in the yield because the star has expanded more. And this is what's really, really neat, because it's the composition that changes the flame speed, that changes how much expansion before the detonation, that changes how bright the thing is going to be. And lo and behold, here is a plot. This is metallicity, but you could think composition. All results are in red. Other preliminary results are in blue. But the observations are in black. And we agree with that trend that as you go to more metals, more things like neon in the composition of the white dwarf, the events are dimmer. And that's an observed trend that we've been able to explain theoretically by changing the flame speed to our subgrid scale model and changing when the detonation occurs. Chirp, chirp, chirp. So, others did this followed this up in 3D and found the same things. We did some 3D simulations as well. Okay, the last piece of the puzzle. I showed you that 3-stage flame model, the consumption of carbon, the relaxation to silicon group stuff, the NSE. That only estimates the energy release and average composition. But how do you know things of like how much calcium you get? How much nickel 56 versus iron 54? And the answer is that what you want to do to get that is put tracer particles in your simulation that get detailed density and temperature histories, and then process that with a detailed reaction network to describe the results. And I'll just say that that's a very complicated procedure, and here's the result from it. These are simulation times versus progress for that reaction variable. The black is what the simulations get, but the red is where Dean Townsley reconstructed it based on basic numerical or direct numerical simulations of the actual burning at scales. Because with this stick flame, even when there's a shock propagating through, you're not resolving it, so you wind up with a longer time scale for what should be a short transition, and that affects the burning. And so you can post-process tracer particles to get detailed abundances, and then here is the spectrum. This is the wavelength in angstroms. 65, 63, H alpha is right here. Although H isn't on this diagram. But you can look at the effects of the different elements going all the way from carbon and oxygen to nickel on the spectral features that you see, because you have those detailed abundances from post-processing the tracers. And these are what we called knockout spectra, and I should have labeled this Miles et al., because Dean student Broxton Miles did this. But basically, you take a radiation transfer code, you have this expanding remnant, you integrate lines of sight through it, and then what you can do is change it by turning off the contribution from a particular element and see how that changes the spectrum, and then you can reconstruct what you actually are seeing. And that is how you go from a white dwarf, a flame model, all the way to matching those observations. And with that, we'll get to questions and discussion. Thank you. So that was a lot of information and a lot of vocabulary, and I'm sure a few people caught a couple of Z's, which is, in my mind, sporting. But I want you to take home the play within the play, that when you can't resolve something like a flame front, you have to construct a model that affects your macroscopic simulation appropriately. You have to verify and validate that as best you can. And then, even when you've got a working model, you may have to do an additional step of post-processing the results to do things like get detailed abundances and then connect to the observations. That's the meta theater, the play within the play. And that's a recurring theme, be it a large engineering application or anything in in the realm of multi-scale multi-physics modeling. Look at that, even a little bit early. Questions on anything?
Just out of curiosity, what's the characteristic turbulent length scale for the simulation?
So that is a good question. And the resolution that we can do is on the order at highest of kilometers. And at that scale, the Rayleigh-Taylor is going and generating turbulence. So it's going from scales on down physically all the way to the dissipation scale. Does that answer the question? I mean,
It does. So you use a sample model, right?
Yep.
I don't know if you mentioned the sample model for chemistry, but
I didn't. It's the model of Cullen et al. And I'm not sure if it was chemistry or some sort of atmospheric application, but it was one that Aaron just looked in the literature and said, hey, I can get a handle on that. And it basically does a local test of the differences in velocities and gradients and things like that, and then assumes that implies so much turbulent, and it boosts the flame speed accordingly. Other choices, they actually have like a dynamical model that you're evolving along with the simulation, and from that you extract the properties. But there's this, I think it fundamentally assumes what's known as Dam-Kohler scaling, which basically says that the flame speed is going to be on the order of the turbulent intensity. It scales from that. And so these are models that calculate that turbulent intensity.
Do you know in advance where the shock is?
So you set up the initial conditions, and then it just propagates. And you can do some things like, for example, I don't want you to think I pulled a fast one on you, but in these simulations, we ran a whole suite of 2D simulations because it's a deeply nonlinear problem, and in order to get a trend, you have to run tens of simulations because where the plumes and stuff go. But we we set things so that there wasn't a plume. This is a 2D simulation, so this is a boundary condition. And if you have a plume on the boundary condition, it reflects and it just zooms right up there, and that's not physical. So the answer is that if you do a full 3D simulation, you set up your initial conditions and let it go, and it should behave like this stuff over here. So all you know is that the shock, or in this case the deflagration, propagates at a certain speed, and then it's up to just the random nature of the fluid instabilities to say where it gets to.
So you have no linear partial differential equations?
Yes.
So,
Yes.
And, so they are elliptic or hyperbolic type?
So they're both. The Euler equations describing the hydrodynamics are hyperbolic, but when you start solving the Poisson equation for the self-gravity, that's elliptic, and you have to do that. And then if you go into things like try to do low Mach number flow, there are things in between. That really is approaching an elliptic problem.
But when you can transition between elliptic to hyperbolic, that's...
Well, it's not really, perhaps I shouldn't say that. The fundamental equations describing the hydrodynamics are hyperbolic. Okay. We also solve an elliptic equation for gravity, but there isn't really a transition between one and the other. The hydrodynamics describes, the flame model is described with that ADR scheme, but that drives the hydrodynamics. And the shock, you can actually simulate that. It's thermally activated burning, but you're not properly resolving it. But the hyperbolic Euler equations will capture that. So like that two-dimensional shock that I showed you, that was a direct numerical simulation of the Euler equations. There's no elliptic solve in there at all. Well, I hope people got something out of that. I probably was a bit ambitious, but that's the story of a subgrid model to blow up and actually connect with the observations of a star. So, thank you very much.
Thank you for that. I enjoyed it.
Oh, good. I was hoping you would get something out of it.
Yeah, of course I did. It was very nice. Yeah, I had nothing. I hadn't seen any of that before, so it was very good.
Okay.
Very nice. I like it.
Okay, good. Thanks. Well, how was that?
I've not used these before. Yeah, I think that went well. I like seeing the spots from Brook and Messer.
To show the background on some of this stuff?
Yeah. I want to ask a question on one of those plots that I'm looking at. Was your plot?
That's what this is.